This is a great problem. So let me tell you the problem, and then I'll tell you the backstory, and then we're going to solve it 2 ways. It's going to be so cool. Trust me on this one. So the problem is, suppose you have a mass, and you have it on the Earth, and there's a tunnel that goes all the way through the center of the Earth, and you want to drop it. So it comes and it falls over to the other side of the Earth, which it will, if you had a tunnel. And then you have another object orbiting at the radius of the Earth, which right on the surface. Which one would get there first? Okay, which one would get to the other side first? Orbit around the Earth, tunnel through the Earth. Now, the backstory. So this is part of my astrophysics course. We're doing gravity, and I did in my previous video, which was very popular, I think, and also very awesome, I did Gauss's law for gravity and found the gravitational field on the inside and outside of the Earth. And we're going to use the Python numerical calculation with random numbers at the end of this to model this situation. That's the awesome part. I mean, it's a pretty good problem too, because it's surprisingly solvable if you assume the density of the Earth is constant, which it totally is not. Okay, so let's do this problem using Gauss's law for gravity. Okay, so I'm not going to go into all the details of Gauss's law for gravity. I already derived the gravitational field in the center, but I'm going to redo it just so it's a full problem in one video. You have the whole thing. You don't have to go to another video. But if you can, if you want to, and you should. Because I'm going to use that code from the previous video. I'm not going to rebuild that from scratch. So there's that. I'm going to take it exactly where we left off. Let's just get to the problem. What am I talking for? Okay. So here I have the Earth, and there's my tunnel, and there's my gravitational field. So if I drop this ball, the thing is, like, as it moves towards the center of the Earth, the gravitational field is going to decrease until it gets to the center where the gravitational field is 0. If you put a mass in the center of the Earth, all the pieces of the mass pull in all the different directions and they add up to 0. Okay. Gauss's law for gravity says that actually only the mass inside of a sphere matters, right? So if I draw a little, a Gaussian, I'm going to start with my picture because I don't like the tunnel. So here's my Earth, and I want to find the gravitational field at this distance r away. I can draw a Gaussian surface. And the only mass that matters for the gravitational field is the mass inside of this sphere. Now, why would I pick a sphere? Because I need to pick something with symmetry that matches the gravitational field so I can do that integral. Okay, so if I assume the gravitational field is symmetric, spherically symmetric, and why wouldn't I, then this integral over the gravitational flux over that surface area is just the gravitational field times the surface area of that sphere. Okay, so this integral over this radius of r is just going to be a scalar, g, times the closed integral of dA, which is just the area of the surface area of a sphere. So it's going to be g 4 pi r squared. And then on this other side, I have 4 pi g mass in. So the mass inside of that is a ratio of the total mass to the total volume. Okay, so here's my radius r, mass m. So I can say the total volume, the total mass m over the total volume, 4/3 pi r cubed is the mass in divided by the volume of the interior r cubed. Okay, so that cancels. And if I solve for mn, I get mn equals r cubed over r cubed. So you notice how I say that, r cubed over r cubed. That way you know it's capital. Okay, m. And so if I put that in up here, I get g, that 4 pi cancels that 4 pi, equals g, capital G, again, mass n, which is going to be r cubed m over r cubed. And then I have this divided by r squared. So I get g as a function of r is going to be g m over r cubed r, and I did that before. Okay, and then at the surface we just put r as capital R, and we can do that. So that's my gravitational field. Okay, now I can use that to calculate the force as an object moves through the center of the Earth. Let me first, so we have, I'm going to put that over here. It's important. G of r is g m over r cubed r. And I can erase this other stuff. Now I want to do the race, right? So I'm going to start with this mass right here. It's going to be moving and orbiting around the surface of the Earth. There's only one force on that mass, and that's this gravitational force. So I'm going to write the magnitude of that gravitational force, F, is going to be equal to g, mass of the Earth's mass, over r squared. I said squared and I wrote cubed. R squared, and that's going to be equal to mass times acceleration. Now, there's only one force, so that force has to have the same direction as the acceleration. And that acceleration, if it's moving in a circle, is centripetal acceleration. So that would be m omega squared r. And so you can write it as v squared over r omega squared r. Not going to derive centripetal acceleration. Hopefully you've seen that before. So let's solve this for omega. So omega squared is, that mass cancels, is g m over r cubed. And then I can put in at the orbital radius of the Earth, r, then omega orbit is the square root of g m over r cubed. So that's the angular velocity for how long it'll take to go as it moves around. And you could say, well, what's the orbital period? Well, that's going to be 2 pi over the period orbital. So I could solve that if I wanted to. T orbital is going to be equal to 2 pi times the square root of r cubed over gm. That's right? Yeah. Okay, so let's put that over here. Let's put omega orbit is the square root of gm over r cubed. And, you know, I'm just doing the plain stuff right now. The awesome stuff's coming. So don't leave yet. Don't leave. Just telling you. This is one of those things where I did it just to see if it worked, and it worked, and I was pretty excited. Okay. And maybe you know where I'm going to go, but don't tell anyone else. So t orbit is going to be 2 pi square root of r cubed over gm. Okay, so I got that. That's your physics 1 question, right? Now this next question isn't actually hard. So suppose that I have my Earth. I'm going to redraw it because I want to. And this is my x-axis. Here's the Earth. Here's my mass. And I know that I have a force, F, is mg. But now I can write g as a function of x, right? So it's going to be in the negative x direction. So it's going to be negative g m over r cubed x. That's a cubed. That's my gravitational force. And that is equal to mass times acceleration, m. I'm going to write this as x double dot, right? So remember that we use x double dot. Ooh, can you see that? X dot is dx dt. X double dot is dx dot dt. So there's a second derivative. It's just the dot notation. Don't freak out if you haven't seen that before. It's not a big deal. It just means second derivative. So I have here a problem, right? Because it's a differential equation that says the acceleration depends on the position, but the position depends on the velocity, and the velocity depends on the acceleration. So it's like, I can't do this problem. Well, you know you can. So let's, oh, there's another mass right there, right? Because that was a gravitational field. It's mg, so I left that off, but that cancels. So I can rewrite this as x double dot negative g m over r cubed x. I just put it the other way. And so think about what this says. This says, hey, if I have some function of x and I take the derivative twice, I get the same function back with a negative constant. So what functions can we take derivatives of and get a negative function back, the same function back? Yeah, you've probably seen this before, okay? And there's more than one solution. But I'm going to go with the most common one. X is a function of t as a cosine omega t plus b sine omega t. That's parentheses. And let's just check, right? If I take the derivative of this, I get the derivative of cosine is going to be negative sine, but I have to take the derivative of the inside. So I get negative a omega sine omega t. And then here I get plus b cosine omega t. Nice. Now I take the derivative again, x double dot of function of t. Now I get the derivative of sine is going to be cosine, so I get negative a omega squared. That's important. Cosine omega t plus, no, minus b omega squared sine omega t. So this is equal to omega squared times x, right? Because if I factor out the negative omega squared times x. So that means that if this is true, then omega squared has to be that. So omega squared is g m over r cubed. Or omega, wait, where have I seen that? Where have I seen that? It's right there. It's the same thing. It's the same thing. So you don't even have to find the period, right? The time it takes to go around is the same as the time it takes to go through. Now, if you want to get this as a function, if you want to write it as a function, which you don't have to, you could say, okay, I'm going to plug in my initial conditions. X of 0 equals r. X dot of 0 equals 0. I release it from rest. In that case, a would be r, and b would be 0. So that term goes away. But you don't have to do that. Okay. Once you get this, you may even say, hey, simple harmonic oscillator, I've seen that before. I'm fine with that. But you really should see why that is a solution, right? Because if we guess a solution and it fits a differential equation, that works. So that's the traditional problem. Now, just a quick note. What if it's not a uniform density Earth? Because the Earth's not uniform density. Well, in that case, this function of the density here would not, when you decrease your r, you wouldn't have a mass proportional to r cubed, right? It would be different. It'd be some other density function in there. And so you'd have to do it differently. And it wouldn't work. Imagine that if you have most of the mass concentrated in the center of the Earth, which you do, then as you move closer to the center of the Earth, your gravitational field would increase it wouldn't necessarily decrease, right? Because you're getting closer to a mass, but the mass isn't really decreasing. Okay, so now let's do the awesome part. Okay, we know the answer. I don't even have to copy that down because I know it's the same as that. So in the previous video, what I did was I took my Earth and I wanted to find, let's say, the gravitational field, let's say at this point right here. And I represented the Earth as a bunch of random point masses. I think I used 1,000. And then I just calculated the gravitational field at due to all these points, right? So it's going to be adding up all these vector values of the gravitational field. And that worked just fine. It was kind of cool. And so what if I use my 1,000 masses to represent the Earth, and I have a ball, and I just let it fall through those masses. Now, that ball is not going to pull in those masses, just the masses will calculate the gravitational field, and we can see what happens. So we're going to have our 1,000 points, we're going to let the ball move through, and then we can have another ball orbit around. And we'll see if they do indeed match. It's going to be great. Trust me, it's going to be great. So let's jump over to Python. This is the code as I left it. I copied it so I wouldn't edit that. But this is my actual code, so we do need to change it up. Let me just show you where we left off in case you didn't see that. So this is Web v Python. If you haven't seen Web v Python, you don't need to import modules. It's already there. It has three-dimensional stuff. I don't know how much of an advertisement I need to give for Web v Python because I just think it's so super awesome, but that's fine. So here, let's play this. Play. Run. So this is actually what I did was I calculated 1,000 points and I made a shell. I ended up making a shell for the Earth to show that if all the mass is concentrated on the surface, then the gravitational field inside is 0. So see, there's my 1,000 points. You can go inside and things like that. But what you want to look at is this plot, which turned out super nice, way nicer than I thought. So this is the gravitational field as a function of distance from the origin. So once you get up to the surface, I actually have a finite thickness, then it jumps up, and then right here it decays down like 1 over r squared, which is what you'd expect. Kind of cool. So I need to switch this back to a full solid Earth. That's the first thing I'm going to do. And then the next thing I'm going to do is to to make a function to calculate the gravitational field. Because remember, I want to take my mass and calculate the force on it and then use that to update the momentum and so forth like that. That's my normal numerical model. Okay, I guess I should, let's do this. I'll switch the board, give you a real quick reminder of how to do that. I don't need the graph, but let's just leave it there. Oh, I had 5,000 points. That's fine. So down here, what I did was I created a random value, right? In Web v Python, we only have one random number function, and it says produce a number between 0 and 1. So if I do 2 times random minus 1, I get from -1 to 1. And then I just say, okay, that would be a cube, right? I don't want to make a cube. So I cut off all the things that don't fit in a sphere, and I throw it away. In this case, I cut off if they were not in between r and r minus dr. So I don't want a shell. So it's really easy. I just delete this. Delete. And then I can run it. Let's see if that gives me, and I don't need this stuff right here. Let's just comment that out. We'll come back to that. Okay, so now I have 1,000 points just like that. I want to make the points a little bit smaller just so we can see what's going on a little bit better. So these are, I did r divided by 50. Let's do r divided by 100, see if that looks, how that looks. Because I want to be able to see inside of it. Okay, that's better. I like that. Cool. Zoom in, zoom out. Okay, you're required to do that. It's just, it's a thing. You have to. Okay, so I have this function, I have this list of positions, RS, right? That's all my masses in 5,000 masses. It's a list of 5,000 things long. And what I want to do, I don't want to every time step re-go through all the masses. Well, I am going to do that, but I don't want to have the code to go through that. I want to make a function that just says, I'm going to give you my position, and then you give me my gravitational field. Let me just remind you how that works on the board. I want you to understand how that works. So if we switch over here to the board, let's imagine that I have just one mass. So here's my mass. I'm going to call it Rm, the location of my mass. And here's my observation location, ROBS. That's where I want to find the gravitational field. I want to find this vector, R. So R is ROBS, observation location, minus Rm. And then the gravitational field, just due to that mass, I'm going to call it dg, right? Because that's just a mass dm. It's just one of the masses. It's going to be equal to negative g dm r hat over the magnitude of r squared. So I need to find that vector r from each mass to my observation location, and then I can plug it in and find g, dg. And then I'm just going to, my g is just going to be the sum of dg. I'm going to add up all my dg's. And that's what I'm going to do. Okay. Back to Python. Okay, so let's make a function. I have my list. I'm going to make my function. I'm going to make it. I'm going to call it, I'm going to get rid of this because I don't want to use g. I'm going to call this function def g. And I want to pass to it a location. I'm going to call it ro because I use r. I don't like to reuse my ROBS. I'm going to call it RO in this function. Now this function, I am cheating. I'm not importing my list of values. I technically should do that. I'm just going to use the global list RS. So what I want to do is to go through my RS values. First thing I'm going to do is say GT, temporary G is vector 0, 0, 0. So once I calculate DG, in order to add it to my total, I have to have a total to add it to. So I have to start at the beginning of the function, I have to have a 0 vector, right, that I can add stuff to. Now I want to go through all my masses. So I'm going to say for Rm, do I use Rm up here? In Rs. So Rs is my list of masses. I'm going to go through each individual one and call it Rm. Now I can calculate R. R is going to be equal to RO minus RM. Now I can calculate dg. dg is negative g times dm, which is a global variable, right? It's up here. It's the total mass divided by n, times norm r. Norm is a unit vector in the r direction, divided by mag r squared. Now I want to add that value to my total. G equals, no, GT. GT equals GT plus DG. And then that's it. So then once I get done, I'm going to return GT. So let's just test if it works, right? I know that the gravitational field on the surface of the Earth should be negative 9.8. So let's put it on the x-axis. I'm just going to print G of the vector R0, 0. Let's just see if that works. You know, when you make a function, you want to test things to make sure they work. And so I get negative 8 points. So I do get something very close to 9.8. It's a random number. So you know you can get some weird things happening, but I'm okay with that. This is an okay function. So it seems like it's working, right? Because if I have it in the negative x, if it's on the positive x direction on the Earth, then that should be in the negative x direction. I think that's fine. Okay. So now I have my function. Let's talk about what I'm going to do. I'm going to switch back to the board and give you a brief review of numerical models. So I can calculate that gravitational field now, right? So here I have my mass. I'm going to say it has a momentum, initial momentum of 0, 0, 0. And it has a position, I'll just call it RB. It's a ball. RB is R0, 0. I can calculate the force on that. F is just going to be mg. G is not constant, right? That's my function. So I have to calculate that, but I can get the force. Now, if I say delta t, let's just say it's 0.1 seconds. I don't know if that's too big or too small, but in the grand scheme of things, over 0.1 seconds, that force is going to make the object increase in speed and move. But if it's a short time interval, I can assume those are constant. So I can say F is delta P over delta T, which is P2 minus P1 over delta T. So that's momentum at the beginning of the time interval. That's the momentum at the end of the time interval. So I can solve that P2, P1 plus F delta T. Now I can do the same thing for position. I can assume the velocity is constant, and I can get the following. RB2 equals RB1 plus P2 over m delta t. So what I'm going to do is to calculate the gravitational force, update the momentum, update the position, update time, go back up and do it again. Because now once it moves, the gravitational field is going to be different, the force is going to be different, and everything like that. Okay, so let's do that. Let's put a ball there, and we're going to give it some properties, and we're going to calculate everything. It's going to be awesome. Okay, so I am up here. Let's just do it down here. I don't need to print that anymore. I don't even need this stuff down here. That was I got all that, right? Okay, so let's make a ball. I'm going to call it ball 1. It's a sphere. Its position is, I'm going to put it on the x-axis. Position is going to be equal to a vector r0, 0. Radius, let's put it at r over 20 so I can see it. And you can't see it because my big head's in the way. Let's give it a color. Color equals color.yellow. And let's do make trail equals true. Now I do need a mass, so it doesn't really matter, you know that. Ball1.m equals 1. Let's give it a momentum. Ball1.p equals ball1.m times vector 0, 0, 0. Right. So I need to give it an initial momentum so I can change momentum. Now I need t equals 0. dt is 0.1. I'm going to run this as a while loop, a time while loop, and I already know, you can play around with this. I know it should take 90 minutes to orbit. I just remember that. The space station orbits in 90 minutes. So let's run it for 90 minutes. So while t is less than 90 times 60, right? That would be in seconds. Rate, let's put this at 1,000. I don't know. Let's put it at Yeah, 1,000. So rate says don't do more than 1,000 calculations per second. We have a lot of stuff going on here, right? So every second I go through this loop, I have to go through every one of those 5,000 point masses and calculate the gravitational field. So, you can get to the part where it's like, I don't think I'm going to run that fast. I can't do it. If I'm just saying, do the best you can. If you can do 1,000, that's fine, but don't go over that. Okay, so now I want to calculate the force. This is actually pretty easy. I'm gonna call it F1. F1 is going to be equal to ball1 dot m times g, and what's the observation position? It's the location of ball 1. So I'm going to pass ball1 dot pos, ball1 dot pos, as my vector location. So that's going to give me my gravitational field there, multiplied by the mass. Awesome. Now I'm going to update the momentum, ball1 dot p, ball1 dot p plus F1 times et. Now I need to update the position, ball1 dot pos, ball1 dot pos plus ball1 dot p times et divided by ball1 dot m. Now I need to update time, t equals t plus dt. Okay, I don't know that it's going to work. Things can happen. I'm just warning you. I'm not trying to set you up for something awesome to happen when things bad can happen too. So that's what happens when you make programs. I'm going to save it though, because I always forget to save it. And now I'm going to run it. There's my ball. It is moving. You see that? I think it's just going slow. Okay, let's, I think it's going okay. I think I need to increase my, my time step. Let's see what I did before. I had a time step of 0.5. And I had a time step of 0.5 and a rate of 1,000. Okay, so it's not leaving a trail. Okay, maybe I got that make trail thing off wrong. Okay, so make trail, make trial. Okay, and let's put this at 0.5, so it'll run faster. Because no one's got time to sit around and wait for stuff to happen. There it goes. Okay, it's falling. Now you'll notice that it doesn't fall straight because these are randomly distributed values, and the center of mass might not be at the center of the Earth. This is going kind of through, got all the way to the other side, and here it's going to come back. I mean, that's just plain cool. Okay, now we're going to put another ball right here, and this other ball is going to orbit the Earth. Okay, so let's think for a moment. Do we need to recalculate the velocity as a function of, well, if I know omega, I know my omega orbit, and I can just say omega is, or v is omega times r, right? So I could do that. So it's just going to be g m over r. I'm pointing at the board and you can't see it. Okay, so we can do that. So let's just make our second ball down here. I'm going to copy everything. Copy all that. And I'm going to, oh, what did I do? Let's just copy this. I don't know if this is a good idea. Copy that. And then paste. And then I'm going to just change this to 2. And I want, it's going to be the same position, same things, except I'm going to make it a different color so we can tell it apart. So let's go with magenta. Magenta, which I always misspell for some reason. Make trail, ball 2, ball 2. Now the velocity, let's just call this VO for the orbital velocity. It's the square root of g times m over r squared. No, not squared. Squared. Oops. Squared. And then this is going to be in the y direction. So this is going to be VO. Oh no, VO for orbit. So then down here, I need to calculate the force on that. F2 equals ball 2 dot m times g times ball 2 dot pos. No, not times. Of. It's a function. And then I need to update the momentum of ball 2. Ball 2 dot p equals ball 2 dot p plus F2 times et, and then I need to update the position. Ball 2 dot pos, ball 2 dot pos plus ball 2 dot p times et divided by ball 2 dot m, and here we go. What do you think? Think it's going to work? What's the percent of it working? Okay, there's my orbital. Why is it falling? Did I not give it initial velocity? Ball 2 dot, ball 2 dot m. Well, that's just fine. Ball 2 dot p vector 0 v0 square root of gm I got the ball 2 dot p ball 2 dot pos. Why is it not orbiting? What the heck? What did I do wrong? Well, that's really weird. Okay, someone probably sees my error right away. Just check square root gm. Oh, it's gm over r. That's why. There we go. So there's my orbiter. Oops. See, it's going around. And, you know, it's funny because outside that looks very well behaved because you're outside all of those masses. It turns out, and this one's going really straight this time. Every time you run it, it's going to be a little bit different, right? So we're going to zoom over here to the other side of the Earth. Which one's going to get there first? It's going to be close. It's going to be close. Ooh, look at that. I mean, come on. That's just right on top. You couldn't ask it to be better than that. I mean, you could, but I mean, that's just not fair to ask that. So, okay, so there you go. Now, if you wanted to, you could plot the position as a function of time. You could show that it is a trig function. You could do a bunch of other things. One of the things that I was thinking about is like, hey, can I make a random non-uniform distribution for the mass in the center of the Earth so that they're not uniformly distributed? That'd be kind of cool. You could say, well, is the center of mass actually at the center? How far off is it? You could do a whole bunch of things like that. You could plot the density as a function of position. Is the density constant, which I assumed it should be. So there's a whole bunch of cool stuff. I really like this animation though. Pretty pumped up about that. So the code for this is down below. A link to my previous Gauss's video is down below. I've had a great time. I hope you've had fun. Really, I'm just so impressed and happy with this animation. I think it's really cool. But play with it. See what happens. Break it. You can't learn until you break things. So there you go. I'll talk to you guys later. I got to stop it. Stop it. There you go. Bye.